Welcome Professor Eric Xing, who is the president of Mohammed bin Zayed University of Artificial Intelligence. So before his starting his talk, I would like to introduce Eric briefly. Eric Xing is a major figure in machine learning and artificial intelligence. He has an exceptional career spanning over 3 decades now, not only in artificial intelligence, but also computational biology and data science. He's both someone with a very great academic record, but he's also an entrepreneur. He had several startups which are very successful. Over the years, Eric has made very important contributions to the foundation of modern machine learning, or AI, starting with probabilistic modeling. He was doing a lot on Bayesian network in the 80s and later large-scale inference. And most likely now is very involved in foundation generative AI, foundation model to answer major scientific questions. Eric is also the first president of Mohammed bin Zayed University of AI, where he has shaped the development of one of the world's most ambitious AI university. Eric is also played a major role in shaping the field through his research, through his leadership, and through the many students and colleagues he has influenced over the years. It's a real privilege to have him today to first talk about this work on world model and also to interact with Yann later in the afternoon. So please join me in welcoming Eric, and I leave you the floor.
Hello, can everybody hear me? Can you text me a signal? I couldn't see the response. Are you guys seeing my computer and also hearing my voice well? Please speak up. Sorry, I didn't hear anything. Anything
yes,
wrong with
Eric,
it?
we can hear you.
Oh, you can hear me. Okay, great.
Yes. Thank you.
Thank you very much. Well, thank you for the introduction, Eric. It's a great privilege and honor for me to be a speaker in your program. Unfortunately, I was originally planning to come in person, but due to the situation in Middle East, I have to do it remotely. So bear with me if there are any audio or visual issues. So the title of my talk today, I have 2 titles. Broadly speaking, I'm going to talk about our recent work toward the next generation AI systems beyond what I call book intelligence. You will see what that means in a few minutes. And then, of course, the focus will be on the PEN word model, which is a stateful, manipulatable and long horizon word model for reasoning, planning, and thought experience. In fact, the background, a movie that brought many famous artworks alive was actually the simulation, from the PEN model, because as a word model, its main function is to simulate real and imaginary world. And that's what actually you'll see from those simulations. Now let's go back to the background of this body of work. So why we even care about building more foundation models and more architectures, for artificial intelligence? Because, in my opinion, the current models, are oftentimes not powerful enough. For example, let's ask this question, how well do current large models understand and reason about the world, right? So this is a picture that I like to share. I ask you, is this person, this guy, on the right-hand side trying to help that lady or not? I guess as a normal human being, we have no problem in figuring out, in fact, take no time for us to figure out, whether he is helpful or not. But if you pose the same question to, say, the advanced large language models like ChatGPT-5, for example, here is the answer you'll get. It believes that this person actually is helping rather than playing, some bad things against that girl. Well, maybe ChatGPT-5 is not the most powerful model. Let's, or maybe I'm not given more time to think. Let's ask a more advanced version called ChatGPT-5 Thinking, which is specialized GPT models for reasoning. After spending 16 seconds, reasoning about the situation, he still conclude that he appears to be helping. So that's kind of a anecdotal instance about how powerful, our current models is in solving real-world reasoning problems. There are other more kind of parameterized problems that you can use to test, the capability. For example, there is a problem set called the detection of motion processing, and you can ask whether these two objects are moving at the same trajectory, and the answer from 01 or 03 is actually yes, which is obviously a wrong answer. Right, and you can also ask a spatial understanding question, say, are these purple, objects and the red objects, of the same size? Or you can ask a positional question like the left and the right, are they of the same size? Again, you don't always get the right answer. In fact, you can systematically test many of such so-called word model automatic benchmarks to testing, ability to perceive the word or to predict the word. And by and large, many of the state-of-the-art models are still quite far, from what human can do in those spatial and physical reasoning, simple ones like you see before. Now, given that kind of testing results, why we still believe that modern artificial intelligence systems are very smart and very intelligent? For example, they can solve a math problem and win a Olympic gold medal, in the MO, right? In a sense, I want to first, break down even the definition of intelligence, because this is a very subjective character of a human being rather than a objective metric of a system. Therefore, whether it is a useful metric to measure quality of the system is in question. For example, we believe Einstein is very intelligent, right? Why? Because you can say that he has a very deep insight in the universe. He's very good at mathematics and so forth. And we all agree that he has a very bad memory, but he's very good at reasoning. So bad memory, isn't indicating intelligence issue, but reasoning is a hallmark of intelligence, right? But on the other hand, we can also, ask: is Mozart, Wolfgang Mozart, the composer, intelligent or not? Obviously, we all believe he's very intelligent, but why he was, becoming famous in the first place? Well, the story carries that in his young age, maybe at the age of pre-teen, 7 maybe, he went to Vatican and heard, from the cathedral, a basilica, a piece of music. And that music was sacred, was forbidden to be copied outside of basilica. But he actually, just by listening once, he could come out and reproduce the score with very good memory. And then he was declared a genius and even get a knighthood from the Pope. So good memory is, sometimes celebrated as good intelligence. Therefore, intelligence is something that is not necessarily objective, in different people's eye. So maybe there's a need to even begin our quest by redefining what is intelligence. For example, here I want to propose that we define intelligence in terms of capability, measurable capability, and utility. We use purpose, not sensation or stance, to define the degree of intelligence, right? And this spirit has been now carrying, a lot of wings. For example, recently in a post from the famous mathematician Terry Tao, he studied, the intelligence system, the GPTs, in a sense, using, a lens from a utility standpoint of view. He said that, the AI assistant was very intelligent, maybe for some small scale, very useful for some scale, and somewhat unhelpful at a medium scale and become useful again and helpful again in larger scales. So the definition is really on utility rather than really sensation and the feeling, right? And the utility is really a very, very defining feature. We define our own needs and also our capability. We're all familiar with this Maslow's pyramid of capability. And using that kind of philosophy or mindset, you could easily define the utility of a individual or maybe as a system using such a similar pyramid, such as the ability to read and write, and the ability to listen and react, doing logical reasoning, planning, execution, and so on and so forth, right? So you could use this as a benchmark to measure not just people but also system. And here is how I see the problem start to break down. For example, at the bottom, of this pyramid, we see read and write, and maybe see and draw. And obviously, our GPTs and our current large language models and the vision models seems to be doing quite well already in those space. And at the top, you see something called prophecy. Maybe that's something never achievable by any system unless you have a crystal ball. But what about the middles, right? The middles basically is a space some say already are covered by GPTs and the LLMs, and some disagree. So here is how I see the problem start to break down into different tiers of intelligence. What we see from LLMs and large language models is, in my opinion, a limited form of intelligence because they only operate in the space of language. You could call them book intelligence because even though they can solve very advanced math problems, they cannot really tell you how to swim and how to interact with physical world because that requires the knowledge, embodied knowledge, and the physical knowledge of the universe. And that's actually where another level of intelligence, such as displayed in this simulated video, could be reflecting, which actually draw upon knowledge of space and time, of the physical space, and that leads to obviously a model that is not LLM. If you want to put an individual in such a real world, you start to deal with agents and agencies, and that requires the system to be able to communicate, interact, understand self and others, and therefore develop a new level of intelligence, which I would call social intelligence. And above all, you also want to understand nature, study the science, developing new drugs and so forth. And that obviously requires you to have an even extra degree of intelligence, which means curiosity, drivenness, and maybe the ability to ask the right question and so forth, which obviously builds on all the lower level of intelligence, social, physical, and lingual and textual and booking and so forth, right? So I think this is the way I see intelligence breaking down into different tiers, and that's helpful in defining where the model can be positioned against. Let's start from the ultimate intelligence and see what might be a good approach to achieve there, right? So this is one of my favorite sci-fi classics called Dune. I suppose many of you probably are familiar with this book, right? It basically played a major role in inspiring many of the science fiction legendary movies and so forth that we've seen so far. But in this movie, in this fictional novel, one of the central figure is a legendary individual called Krizak, and he has a supernatural capability which can allow him to, say, command armies to win a galactic war, or oversee global scale projects like turning a desert planet into a green paradise and so on and so forth, right? So these are really complicated and big tasks, and which could be the epitome of superintelligence. But what's interesting in this book is that how he achieve and solve these very difficult problems. It turns out that he has this amazing mental capability of simulating outcomes of all possible plans before he even execute. And this simulation capability actually comes from his mental world, which was built from inheriting all the knowledges from their ancestors. So that's actually a very interesting thing because the methodology sounds surprisingly similar, to how we build computers and how we build, maybe repositories of knowledges, right? So the question I want to ask next is that how to build such a system, a superhuman. Maybe building a superhuman of a Quasar is too far a reach, but maybe we could build a system with a similar behavior, and going up the hierarchy of capabilities, like what I saw, I wrote in this pyramid from low to high. And then, that basically leads to a design of a system, which is a goal-oriented agent acting in the environment and achieving goal in a DOM style, which is simulate the plan before you act. And that basically is the setup of my entire presentation in terms of the technical architecture, which start from defining an optimal agent that can solve more and more harder problems. So in an optimal agent, the agent can generate an action upon receiving or seeing a state from the real universe. And then optimal agent means that you want to achieve the goal optimally by maybe maximizing the cumulative reward function. And that leads to a solution which is an optimum policy that maximizes the cumulative rewards. So what's the problem with this system? Well, this system basically means that you need to, among any things, have a direct access to the real universe, which is the world. And that's actually a very difficult thing. For example, how can we train, an astronaut or maybe even a robot, to go to the Mars before we even are on Mars? Obviously, you need, to, obtain some capability before you have having access to the universe. And that leads to our second goal, which is that, you can maybe build a model which can simulate the universe as a surrogate. And that is basically where the world model, arises. It is a simulation model that can allow you to simulate the environment so that you can do optimal reasoning. And therefore, my definition of the world model is a generative model that simulates possibilities. These possibilities are not limited to only physical possibilities, such as pouring the water, throwing the objects, the physics of the objects, and so forth. It could also include embodied experiences and emotional experiences, and maybe social experiences, and maybe also a mental world, maybe even counterfactual world, and many other things, right? So imagine such a world model can be built. Then how does it change your way of behaving, planning, for example, strategizing? So this is a proposal. You can reason by simulation rather than solving optimization. What you have from the world model is a generative model of the next state, given the previous state and the action. And then once you are given a goal, for example, you can basically just use this simulator, this world model, to simulate multiple trajectories, and then look ahead and see which trajectory gets you to the goal, and also at the lowest cost, and then you execute. So this is a unique way of reasoning, which is different from what we design many computers to do, which is to do inductive reasoning and solve a big option problem. In here, you reason by simulation. There are books, in fact, about this behavior, such as this one, hypothetical thinking. And in our common language, we call them thought experiment. That's actually most, common individuals, or maybe even great thinkers, used to solve problems, thought experiments, rather than solving a big linear system, a big mathematical equation systems, and so forth. And this approach is highly flexible and repurposable. You may know the system AlphaGo. It is actually, a word model, plus a Go playing agent, which, the word model is the Go board and also the play rules. And then you can simulate upon a board position, multiple outcomes, and then, using a Monte Carlo tree search algorithm to extract the best one. The same algorithm or the system, once you replace the word model with a different one, such as a self-driving word model, a battleground word model, and maybe the Mars model, you actually can use the same simulative reasoning algorithm to solve problems in those space. And the experience learned from such approach with a world model is also highly transferable, as we also experience in our daily life. For example, we train the astronauts who can walk on the moon by letting them to do scuba diving, right, to experience that loss of gravity. A mountaineering athlete could of course be a soldier to command ambush in the mountain regime. And we also know that nowadays good game players could be a good combat soldier because he may be very good at manipulating weapons like drones and other things. So now let's go back to the core question about how to build such a general world model. And here are the four metrics or maybe elements that I found to be key. Representation of the space of latent concepts and word states, architecture to effectively allow you to reason, and also objective function for you to train the model, and then of course how to use it. So I will break down each of these elements more carefully. But because we are also set up a discussion, a debate with Professor Yann LeCun, I also want to present a few alternative approaches, such as I listed here, in terms of addressing all the design questions of a world model I just listed. Here is a proposal. In this particular school of thoughts, it was mentioned that the data to use to train world model should be image rather than text, because text data is too small. Image data are a lot bigger and richer. And also the word states should be continuously embedding rather than discrete, because the continuous representations are very friendly to mathematical manipulations like gradient operations that are efficient. We should use an autoregressive model. We shouldn't use an autoregressive generative model, according to this school, because they, are error prone due to the intractability, of the complex outcome that they have to generate. And also, the loss function shouldn't be data reconstruction loss, as in many generative models, but should be, more like a latent, representation prediction problem. And then how to use it? There are proposals like MPC, model predictive control. So this is a proposal which I found to be interesting, especially this one, which is that the loss function should be built on latent state prediction rather than data reconstruction. And among many of the recent efforts, there are different implementations of world models that I listed here, which kind of are not all in compliance with the proposal I mentioned earlier, but they also share some commonality, which is that it seems like what they care about is to generate good videos and pictures, rather than focusing on additional functions of a world model, such as deep reasoning through simulation. So in that context, I want to present a body of work that my group have done recently. The idea comes from this paper, Critique of World Models. If you're interested, you can go and read, where I systematically break down, the foundational theoretical insights behind our design. Again, the key, considerations, for building world model is data, representation, model, loss, and usage. And let me discuss each of them one by one a little bit. So on data, yeah, data, text data is very small, as argued, by Yann and many others. The data that we see, even as a child, could be already way exceeding the volume of all the data in text form used to train large language models. However, I want to point out that when we talk about data, it is not just about data volume, it's also about the information density. I would say that text data really give more dense information than pixels, because language is kind of a human embedding of what they see in the real world. And there are complex contents information, such as abstract concepts like regrets and justice, that is very hard to be extracted from video. And also, you use language to enable natural interface of interaction, which is also difficult, through visual cues. Therefore, our proposal, for the training data is to use all modality rather than only text data. And that's the first question, hopefully, rather straightforward. Representation is another issue. The proposal from the JEPA school, propose or prefer a continuous latent representation because they are gradient friendly. However, we also know that continuous sensories can be very, very variable. And also, if for every continuous input you compute an embedding, these embeddings are stateless because they are highly variable and unstable. Therefore, it is not easy to extract semantic meanings out of those embeddings. Just like what I show in this figure, different image kind of patches can hardly leads to a consistent semantic embedding that can be stable upon different appearances of the same content. And therefore, our representational choice is to use a stateful and identifiable semantic latent space to anchor the reasoning in both long-term and short-term memory. And for example, use the words. As I mentioned, the words are human tokens, for embedding already what people see. But also, even for new things that we don't have a word, you can use techniques like VQVAE to convert sensory signals into tokens and so forth. And these representations really enables a more powerful way of capturing information both in continuous embedding and also in discrete tokens. So we keep both of them together. And we also have a theory to prove that in fact, you have the flexibility of building new vocabulary to capture information, even in continuous signals, as close as possible, by playing a trade-off, of the vocabulary size and also encoding length. So for the sake of time, I'm going to skip the technical, theoretical details of that argument and jump to the next dimension, which is architecture. So the architecture debate, on word model is the most interesting one. For example, the JEPA architecture is like what I drew here. It is a encoding architecture, which basically encode the inputs from both the previous time point and next point into latent space. And then you build a word model which makes prediction of the latent space from the previous embedding to next embedding. This is a very interesting architecture which is computationally very, very efficient because the loss function is rather easy to minimize. However, they have some flaws, as I'm going to discuss in the debate. So, for example, there are issues about identifiability, right? And also there are issues about collapsing, which I'm going to mention in a second. So our approach is called a generative latent prediction approach, which is a closed loop, architecture with an encoder to begin with, and then carried through a reasoning backbone, and then a decoder back into the visible space. Of course, they operate on a mixed latent representation. Therefore, in the backbone, you can have a LLM style transformer reasoning backbone, and also a diffusion model like backbone to drive the numerical signals. And this representation of a hierarchical representation, each level can have a proper level of abstractness, and that's basically a representation or a architecture that we propose to use. And one of the main reason other than the capability of reason in mixed representation space is also the more principled trainability and the loss function definition of this architecture. Because when you use JEPA or a latent prediction architecture, you define a loss function that is more optimizable and stable. It turns out that this loss function, which you defined on a pair of latent states, is mathematically yield behaving. It can easily collapse. For example, you can imagine that if I just encode both the previous observation and the next observation, into a constant, then you have a trivial predictor that always does things right? And there are other conditions which can compromise the utility of the encoder and also the predictor, as I will discuss later, in the debate. So what we use is a generative loss, which directly measure the difference between the generated, observation from the decoder against the actual observation that you receive. And it is a well-defined probability motivated loss function. And we can also prove that this generative loss is strictly an upper bound of the latent loss. Therefore, by minimizing this generative loss, you also can minimize the latent loss. But the reverse is not true. When you minimize the latent loss, you do not necessarily minimize the generative loss. And on the usage, once you have a word model, how to use it is another interesting topic that I want to say a few words. The JEPA school proposed a approach of using word model only in the inference time called model predictive control. This is a well-known technique that is used in factory industrial control and so forth. The idea is that once you have a word model, and when you are doing planning or predicting actions, you can always use the word model to simulate a few steps. And then you can solve a bounded optimization problem by finding the best path among the word states and also the simulated actions, and then you pick an action sequence. Well, this is mathematically an elegant approach, but it is very expensive because in many real-world problems, you may be simulating or solving a plan that involves hundreds of steps, and in each step, hundreds of thousands of action options, and that's becoming, a intractable optimization problem under MPC. And also, it has to be done in real time when you actually solve the problem. So our approach in using the word model is a combination of MPC, but also an offline RL algorithm, where when you are not even doing anything as a AI agent, you can still simulate the word model, just in your system, and learn policies, of possible simulated word states and word space. This is more like a Go player, not only learn during the actual play, but also do simulation or self-play, when he's not in a match, and still gain more skill. And we found that the word model gives you that flexibility. And we actually can have a theorem proving that the RL algorithm, that you learned, and then stored in the associated memory as a policy won't compromise, your actual action, when you deal with a real world situation, because you always have the other option of going to, a real, MPC based optimization approach if need to, but you don't have to always go that. So summarize, our word model architecture, which is called the generative latent prediction architecture, is a system like this. It contains it has consistent understanding and prediction of the word states, and it is a generalist high-level word dynamics plus a low-level perception details. So two type of reasoning backbones enabled by a large language model pre-trained, and also a multimodal decoder. And then you can also incorporate instruction tuning and action encoding through this backbone. So based on this framework, we recently implemented and released a instance of the word model called PEN. And just as you can see, PEN is a initial version implementation of this architecture, which use a next latent state prediction, but also a integrative diffusion, LLM diffusion architecture, for the reasoning. And it actually predicts, multimodal observations, which allow you to communicate with other agents and also perform generative supervisions. And also the building blocks in each of the components and module here is actually compatible with other, foundation models that you can, obtain, from the community, such as the existing large language models, VLMs, DINOs, and so forth, with a canonical interface. The learning is based on next latent prediction and generative reconstruction, and also reinforcement learning, as I mentioned earlier. Against a particular technical issue, raised by the JEPA approach, which is that reconstruction, of complex visual signals can be expensive. We actually also have some additional technique to mitigate, that computational cost. For example, you can design a particular video diffusion decoder which do partial reconstructions, of the outcome, focusing on only the important elements, through a queuing kind of mechanism that allow you to do reweighting, of different contents. Recently, we also released, developed a new technique, which is working at the infrastructure level, to speed up the very computation, of LLM reasoning and also of a diffusion model based on diffusion distillation, sparse attention, and also fast LLMs. It turns out that this approach is highly efficient, that it can generate, for example, the video 10 times faster than the playout of the video. So for the first time, in the community, we can actually produce video contents faster, than what the video content itself, takes. And this type of technique again can, reduce the cost of, large language of, the GLP architecture of the world model to make it more viable and more able to leverage on complex data. So let me show you some, demonstration, of this PEM model. To qualify as a world model, you must go beyond just the image generation, but enter the world of visual understanding and also visual word simulation. So what understanding mean? It's very hard to really, articulate very clearly, the property of understanding. So here we take a more operational definition, which is the manipulability. You can actually manipulate content through text prompts continuously to drive and steer the production of the contents. For example, here, I have a current state. If I want to go one step forward and say move forward, you see this happening. If I say, go lift off, you see this happening, which kind of tells you that the model actually understands what is in the picture. And depending on what you want to see happening, they will branch out into different next states. You can go further and put some weather conditions. Likewise, you see, a nice, simulation, in compliance, with your prompts. So the PEM model is not a task-specific, model that only focuses on a narrow type of contents. It is very, very diverse and universal. And you can see many of the interesting scenarios, simulated from here. For example, this scenario caught many people's attention because it is simulating, a car behavior. Let's see, I can play it or not. Yeah. This is a video which leads companies like Waymo to be very interested in, because to train an autonomous driving car, you need to have enough video signals to really start illustrating and training, behaviors of rare accidents when you run into that. But such videos are very, very rare if exist, in real world. And therefore, our world model can help to even do data generation of those rare scenarios. Here is another video showing you stepwise manipulability, of the possible words. Again, the video itself is not fascinating like what you see in Sora or Gemini and so forth, but it is a different type of video, which is not pre-scripted, or bulk programmed in a single passage. You can actually go into the video and in any seconds, type in, a new action, a new direction, and the model actually doesn't know what's going to happen next. Only after you type in, they are going to start to simulate what is going on next, which again demonstrate that the model knows what is in the video in terms of a microwave oven, the balls and also the bottles and so forth. Again, we use this type of task to demonstrate understanding, of the possible words. Again, coming to evaluation and demonstration, evaluation benchmarks of word model is actually a problem by itself because the current visual-based so-called word models really are testing something not so fundamental to a word simulator. For example, they test short-term, short horizon metrics like frame depth fidelity, or motion realism and so forth, which of course is cute and useful for high video quality, but they have very little value to generate long horizontally consistent scenes for reasoning and planning. So we come up with a new set of benchmarks which measures long horizon consistency, high level controllability, and also planning qualities. And this is basically a set of more explicit definition of those metrics: action simulation, long horizon forecast, and the scenario planning and the reasoning. Again, among these tasks, we see very few models able to achieve very good score because that's exactly what the current models have been largely ignoring. So our paper did a very systematic comparison of for example action simulation fidelity, long horizon forecast, and the simulation reasoning. Especially the simulation reasoning, you simulate to solve a problem rather than to generate a pretty video stream. And those kind of functions are rarely, if ever, considered in the past as a quality measure of the word models. So let me just give you a quick kind of demonstration about how these tasks each look like. For example, here is a simulation of what we call long horizon and the branching possibilities. You started from somewhere, and then you can enter different action prompts and steer the movie multiple steps into different next word or next states. For example, you ask the flower to bloom itself, or you do a golden light spell, you light a fire, or you maybe enter a tunnel and so forth. You can really drive the whole possible word further, maybe even indefinitely into the next word, and actually can come back to its original word because the states are it's a stateful simulation. Therefore, the past, the history will actually remembered. So this is useful for you to do simulation of planning and thought experiments. Here is another instance about how to use the word model to solve a problem. So here, for example, the goal is to start from this particular scene where you have 3 beans, and the middle bean had the 4 yellow objects, the 4 yellow cans, and then you have the blue tray on the right, and the middle tray in white, and you want to now achieve an equal split of the beans between the blue tray and the white tray, right? So this is a simple task. How can you actually do simulational reasoning to find the right movement to achieve that? And this is basically what the word model is able to demonstrate. It basically can simulate multiple things, picking the can up, put it right or left, and then next, put it back or continue to pick the next bean and so forth. So there is one path which leads to a equal split of the bean, through a simulation of possible actions and next words, and others failed. So before you do this action physically using a robotic arm, you could already simulate the whole thing very quickly in your brain, and then the arm can now get a proper a sequence of actions to execute this goal. So that's basically how we see the word model to be able to get used, such as leading you out of a complex maze if you get confused or lost your way. Right? So there are a lot of use cases that a PAM model could offer, and here are just examples about how they can be used to simulate, sports, industrial, robotic manufacturing environment, physics, or even social training. And I think this is, really a very promising direction, for world model to pursue, beyond just generating, nice movies. Okay, so I have a few minutes left. I want to go back to, our original goal of super intelligence and super agent. And so now we have a world model, and our goal is to build a goal-oriented agent acting in the environment and achieve goal in a doom fashion. Now the environment is given by the world model already, and what's next? It turns out that this definition of the agent is just as confusing, if not more confusing, than the world model out there, right? For example, there are many agent systems these days, from different companies. I have to say that it may be a little bit inappropriate to really call them agent rather than a pseudo agent, because the main focus of these tools is really automation, finishing a job, use different tools and so forth. Does this really suggest agency? Well, what human agency is? Well, human agency is a very, very different, property. First of all, humans are very versatile. They use one cognitive system to solve all these tasks, which involves, physical intelligence, social intelligence, emotional, and many things. And therefore, it's functionally, it's more versatile, than any of the existing, agent systems that you see, right? In terms of, adaptation, innovation, communication, and continuous learning, and so forth. But even more so, agency, a human agency, a biological agency, had a very, very interesting cognitive element, such as the definition and awareness of self, the boundary between self and others, so that you can define collaboration and teamwork, and also the clear recognition of a goal, and accordingly self-regulation and self-organization and reflection, and so forth. None of the current agent systems had anything to do with these type of qualities. But I think this is really needed if you want to define a truly autonomous agent that can, rely less, on external instructions, and still able to accomplish complex tasks. Therefore, we define, the agent model, with a set of, characteristics and capabilities closer to human agency, such as actively perceive the goal, reason about the purpose, and reason about purposeful actions, and learn from experiences, being able to adapt and generalize, and so forth, right? And so going back to, the element of the agent model, again, here is what we see to be useful: goal, belief, world models, and planning. And I'm going to say, propose again, a draft architecture, for these type of agent models. So I want to start from what's out there already in terms of empowering agent models. There are now two conventional schools of thoughts, for agent models. One is a policy-based kind of approach, which is a fast reaction and built on end-to-end policy models that can output action directly. Right? They have the advantage of being very, very simple, and also being very, very computationally efficient and rapid. They don't maintain a model of the world. It's purely reflective, based on perceived states of the world, and then roll out the action using a policy model. The other approach is a model-based approach, which is actually closer to what Professor Yann LeCun was also advocating, right? Using the world model, to really instruct and guide the agent and to come up with rational actions. Again, the advantage is that it really opened the possibility of long-term reasoning and data efficiency without necessarily to train, a complex policy model. But on the other hand, obviously it is expensive on the other end, because you need to always do simulative reasoning or MPC. Right? I would classify these two approaches, into what we know as the system 1 and the system 2 cognitive reasoning. One is based on prompt price policy, learned from reinforcement learning and do like subconscious reflective kind of activity. The other is more like an inference time planning based on MPC or MCTS, using a model-based approach. I don't think these two should really be put against each other. In fact, I would propose in our model what we call a system 3, which not only can do both, but also have a additional function which we call a regulator or a deliberator, which can instruct the system when to use system 1, which is cheaper but short term, or when to use system 2, which is more expensive but longer term. And that's basically a proposed architecture, which includes a word model that is pre-trained and a policy model that can be trained previously or can continuously be trained, and also a system 3 reasoning, which is a configurator for when to plan or when to plan deliberate or when to stop plan and act directly. So the architecture is a little more complicated. You see the configurator, which will deliberately choose a policy model or a word model depending on the distance or the quality of the effects coming out of the previous action and so forth. And there are other designs that I'm going to skip the details just to wrap up. So to validate this hypothesis, we actually recently also built a prototype of a self-regulatory agent model called SRAM, and which is presented on the right. On the left is a classical LLM agent, which is really a black box that you prompt it, and they will basically do reasoning for you using a unknown thinking path or chain of thoughts. On the right, you have a system that is a white box where the configurator will allow you to deliberately choose when to plan, how much to plan, and also using what intermediate results to replan or to evaluate. And the results shown here shows an interesting contrast. We found that using this system 3 architecture, we were able to achieve very, very complex planning and reasoning behavior with a relatively smaller model, at the capacity, comparable to a model that is 1 or 2 orders of magnitude bigger. As you can see from here, this graph on the x-axis show many models of different parameter sizes, and the y-axis is the score of the performance. You can see that the SRAM model, is comparable in performance to the best model out there, such as the DeepSeek 2 and the Kimi 2.5, which are literally hundreds of times bigger. And this model is only 30 billion parameters. And the way to achieve that is because there is a cost-effective planner in the system that allow you to do more smart planning. And this is another demonstration about the comparison of our agent model compared to other models of comparable sizes. Apple-to-apple comparison, you can see that the reasoning per token is much smaller, and the overall score is strong. Here is an insight about what's happening inside. Right. So in a self-regulatory agent model, you actually started with a much richer initial plan, which allow you to deliberate and replan when necessary, even for a very complex scope. But the overall steps required to arrive at the right solution, in this case, it's a pretty difficult question. It's how many non-indigenous crocodiles were found in the Florida, from some years between. It's a very, very interesting problem that requires you to do planned search and the literature review and the analysis of data in multiple steps. So our model, had a couple of different plans, and at the end of the day, reached to a right answer in 45 steps. Whereas, a model that is not pre-trained with reinforcement learning for the policy, for the configurator, takes much more steps and get the wrong answer. And the external benchmark model that we use in fact, also take longer steps and get the wrong solution. So this is basically what we like to see, how the world model in the future can go hand in hand with the agent model to really go toward a higher level of intelligence. The world model here is really used for perpetual retraining of the agent system in an infinitely possible world. And this is actually a kind of a realization of such a game plan. We already use the PAN world model to build an initial version of the game model where you can simulate long horizon, high fidelity interactive simulation experiences. Long horizon here is important because that's where you really can learn quality policies and also models with enough complexity closer to the real world rollout of complex scenarios. And the world model you can see is really flexible in responding to complex actionable prompts and come up with different outcomes. And accordingly, the agent or the benchmarks can also be built on such a world model, which really measures the system against task completion. In this case, for example, opening the correct door to go in, or find say the parking spot for your vehicles, or find the ice cream selling station out of many possibilities and so forth, right? So you can use the world model to simulate the scenario and the outcome, and then let your agent to be trained. So to wrap up, so this is basically just a beginning. With the world model and the agent model, you can always compound it with some more complex scenarios. For example, a regular world model, when add additional agents into it, becomes a super world model of a physical world plus many agents. And then the super world model can leads to a super agent model, which really think about the world in certain abstractions. For example, economists think about the world as a collective population rather than every individual in terms of financial and economical behaviors. So this type of a nested structure of a super world model and super agent model can allow your planning and the reasoning to go arbitrary level of complexity and granularity. So to sum up, what I presented just now is a roadmap go beyond book intelligence toward physical intelligence and social intelligence and the philosophical intelligence. And I believe that simulational reasoning with the world model is a very promising path toward building true intellectual intelligence and problem-solving capabilities in a very complex scenario, because they are scalable, transferable, and also very, very flexible. They actually can come up with very, very complex scenarios and generating very complex possibilities, even from a simple root models. And that actually give the world model a lot of potential in achieving high performance, even with limited amount of resources. And of course, I talked about the issue about representation learning and architecture, which is still an ongoing debate, which I again look forward to exchange with Yann in the next few hours. That's all for my first talk. Thank you very much.
So thanks a lot, Eric. It was a very great talk, and so we have the time for. So Yann LeCun is already online, but I think he asked us to spend. We have 5 minutes now, so for some preliminary questions, and then I will leave the floor to Yann. So 1 or 2 questions now from the audience. Okay.
Thank you very much, Professor, for your presentation. I was wondering about the architecture of GLP. In slide 34, you were mentioning that you support both symbolic and continuous reasoning. Could you a bit elaborate more about the symbolic parts? Thank you.
the symbolic part is basically a large language model, right? You basically, use the word token, to establish, long horizon chain of events and effects, and then you reason in that space. Then the numerical, continuous reasoning is based on a diffusion model. So you basically have a backbone that builds on pre-trained large language models of choice, and also, diffusion models, of specific domains.
As we have time for another question.
Hello, Eric. My name's Alain Rosen, based in Paris. I was wondering, one of the critiques on world models is the whole notion of causation, that simulation doesn't equal understanding, and it seems like world models are stuck between rung 1 and 2 on the causation kind of ladder that I think Judea Pearl developed. Just wondering, how do you see the development in the months or the year ahead in terms of improving that?
I need to understand it more about what exactly mean by causation, right? And is that the cause, because they have a chain of thoughts which actually form a causal chain, of representations, inside the system. If desired, they can be exposed. In fact, with the word model, you actually could already simulate, possible words, including counterfactual words. Therefore, all the possibilities, that Judea Pearl is imagining, from different configurations of causality, in a sense, in my opinion, can be simulated. But it's where I think word model is, not of course exhaustively, giving you all possibilities, right? But it gives you a computational advantage, of focusing on the high probable outcomes, and then start already, picking the best action sequence based on that.
Okay, so now it's thanks a lot, Eric. Thanks again. So we can a big applaud, I think, and then we need to we will welcome our Yann LeCun. So it's a great pleasure to welcome Yann. So Yann LeCun, everyone knows Yann, so I will be very brief. He's of course one of the central figures in the history of artificial intelligence. His work helped lay the foundation of what is called modern deep learning, and is still very active, so it continues to shape some of the field's most important directions today. Of course, Yann is widely recognized as one of the pioneers of neural networks, especially through his landmark contribution to ConvNets, which played a very major role in bringing machine learning into real-world applications. But beyond these foundational achievements, Yann has remained over the almost 40 years or more of his career one of the clearest and most influential voices in AI. So he has been, of course, awarded by the Turing Award, which is a recognition of his work. What makes his perspective especially important for today's discussion is his very long-standing commitment to a broader vision of intelligence. And he was exposing that, of course, 3 years ago in this room, by the way. So about systems that can learn, that can predict, that can reason and build internal models of the world. So it's a real pleasure to have him with us today. So please join me in welcoming Yann LeCun. So, okay, we have to wait 1 minute, so you have 1 minute to relax. So what will happen? So I will explain. So for a minute, so Yann will give a short talk on his vision of world model, and then we will be a debate between Eric and Yann. So first a debate, and then they will take questions from audience. So the way it will be organized, I will you the microphone, and also please tell who you are. Okay, it's better for them to know whether you are a student or you are a professional, because the way to answer is not exactly the same. So. We have time for one question for Eric, waiting for who has a question. Ah, il est prêt. He's ready. So, okay. So Yann, speech. In now. So we
Hello.
see Yann.
Yeah, see you.
Eric.
So let us speech to speak. Okay, so for the so you can have Yann. You can start if you want to give some quick summary of what's your vision of world model, and then we do the result of the debate. So Eric has spent 1 hour explaining what is his vision, and so you have time now to explain what is your vision, and then we will discuss.
Okay. I guess I have 10 minutes. I have slides, but
yeah, you
I
can.
think I'm not going to use.
Use
Can I use slides?
Yeah, of course.
Well,
Yeah.
but I'm connected to another computer for the slide, but I'm in the waiting room. So
Okay.
If you guys can admit me.
Okay. So you can start. I will go to the regie. So sorry. Okay, you can share screen.
No, it's a different computer. I'm connecting a second time, but I'm in the waiting room.
He has two connections.
Two connections. One is called Yann LeCun présentation.
There's a Yann LeCun presentation. Yes, so this is what we can you retry, Yann? Can you retry your connection?
Okay, sure. Okay, I'll try it again.
Okay, Eric Xing.
You don't see me?
I will go to the regie. so 1 minute.
Okay. Okay, looks like yes. All right. Okay. So sorry for the issues. So I'm going to talk about one model, and I'm going to make an argument that one model must not be generative. And Eric and I have had that discussion before. I don't know if his thinking has evolved on it. I could not listen to his talk before, so I'm not sure what the debate is going to be about. But I'm going to argue for the fact that world models cannot be generative. Okay, so first of all, humans and animals learn world models. That's what we use for planning, for reasoning, for predicting everything. That's what allows us to really act intelligently. And babies learn things during the first few years of life, mostly by observation and of course by interaction. So how do we reproduce this kind of learning with machines that allows babies and animals to learn models of the world? So first of all, we learn this through high bandwidth sensory inputs like vision, like touch, like audio, and other modalities. And this is a far cry from LLMs that learn purely from text. Text is very low bandwidth and it's dense information, but there is a very limited amount of it, something on the order of 10 to the 14 bytes publicly available on the web. Whereas for video, and we have basically an unlimited supply of visual input. So clearly we can get machines to learn a lot more by watching video than by just reading text. So there is the reason why we need world models is because we want to build agentic systems that can plan actions to accomplish particular tasks. And the reason for world models is that you cannot imagine building a reliable agentic system without that agentic system being able to predict the consequences of its own actions. Okay, it's very difficult to act without having the ability to predict the consequences of your actions. You can act in familiar situations, but you cannot act in new situations unless you can predict the consequences of your actions. That's what allows you to plan. So what that means is that you absolutely need world models. There's no way around it. You can make all the arguments you want. In the end, if you have a world model as depicted at the bottom here, let me show a bigger example here. You perceive the world, you get some idea of the current state of the world, perhaps combined with the content of a memory. You feed that to your world model, and your world model, you also feed it a hypothesis for an action sequence that you imagine taking. And what your world model does is that it predicts the the state that will result from this action sequence, or in fact is going to predict the entire trajectory of state resulting from this action sequence. You can feed this predicted states to an objective that computes whether a task has been accomplished or not, and perhaps to a bunch of guardrail objectives that measures to what extent the actions that are being followed are safe or not. And then by optimization, you look for an action sequence that minimizes those objective functions according to the prediction of the world model. Okay, so inference is performed by optimization. So you figure out an optimal action sequence that will satisfy the task objective while satisfying also the guardrail objective, using your world model as the means, as the tool to predict the outcome of your actions. Okay, so inference is by optimization. That's a very important point. Now, all of this has to operate in some abstract representation space that represent the state of the world. And of course, if you have a world model, you can run it multiple times in autoregressive fashion to predict the outcome of a sequence of actions. And ultimately, what you want to build is a hierarchical world model. And I'm coming to this in a second because I think that's a very important concept. When humans and animals plan complex tasks, we don't plan it in terms of elementary actions, which in the case of humans would be millisecond by millisecond muscle control. We plan at a much higher level, and then we work our way down to the low-level actions that are muscle control. But we do plan hierarchically. What that means is that we need our world models to be hierarchical. And so that's a far cry from generative approaches. So a generative model will look at a piece of video, for example, run it through some encoder, and maybe a decoder or a predictor that predicts the rest of the video. Okay, and you would train the system by minimizing some sort of cost function, some discrepancy between the predicted video and the observed continuation of the video. I've been trying to make this work for the last 15 years, and essentially failing for the first 10 of those 15 years, including using all kinds of latent variable models and things like this. This is a note paper that's about 10 years old, and what you see is the predictions that you produce when you train a system to predict videos at the pixel level. The predictions are blurry. And there is really no way around this. One way around it is to use latent variable models, but like diffusion models or things of that type. But it really doesn't solve the problem because most of the information in the video is not predictable. Most of what happens in the real world is not predictable. When you train a model to predict all those things that are not predictable, you kill it. It simply doesn't work very well. If I take a video of the room that everybody is in right now, listening to me, and I point the camera to the left side of the room, and I slowly rotate the camera, and I stop, and I ask the system, tell me what's going to happen next in the video, there is absolutely no way that system can predict at the pixel level what everyone in the room looks like. It's just impossible. The information is just not there. And so you would have to, put this in some latent variable, but then you hit another issue with latent variables. So my solution to this is what I've called JEPA, Joint Embedding Predictive Architecture, which is represented on the right here. And so basically, the idea of JEPA is that you do not attempt to predict pixels. You do not make this a generative model. You encode the part of the video you want to predict, which is the variable y here. And you produce a representation of it called sy. And then what the system does is that it predicts sy from sx. It predicts at the representation level, and it does not attempt to predict every detail at the pixel level. Now, there is a slight complication with training a system like this, which is that the system is happy to collapse. It's gonna, if you just train it to minimize the prediction error, it's going to ignore the inputs and then produce a constant representation. And now the prediction problem becomes trivial because the representations are constant. So you have to prevent that from happening. And basically what you have to do is have some measure of information content for the output of the encoder and attempt to maximize that. And that's the complication in training a JEPA. But we have a bunch of solutions for this now. Now, let me insist on this point that learning hierarchies and abstract representations of the observations is really fundamental. I could, in principle, explain everything that is taking place right now between us in terms of elementary particle physics, or even quantum field theory, or even atomic physics. I could simulate every atom, in the room I'm in and in the room that you are in, and simulate everything at the atomic level, and it would explain everything that takes place. But of course, it would not be a very useful simulation. First, because it would be incredibly expensive, but also because it's very likely that the simulation would quickly diverge from reality. And so we never describe the dynamics of a group of people in terms of atomic theory. We describe it in terms of psychology or sociology or something like that, right? So what I've drawn here is a hierarchy of different abstractions, from quantum fields to particles to atoms, molecules. In the living world, it's proteins, organelles, cells, organisms, individuals, societies, ecosystems. And all of those levels in this hierarchy is a different way of representing reality, which ignores some details about the level below. And this is why we can explain to some extent what goes on when people are talking to each other at the level of psychology, but not at the level of particle physics. Physicists do this all the time. Science does this all the time. In fact, every level in this hierarchy is a different field of science. A field of science is essentially entirely defined by the level of abstraction at which you represent reality. So this idea that you have to find an abstract representation to be able to make predictions, I think, is absolutely fundamental. And that essentially destroys the whole idea of generative models. What can we use those JEPA world models for? An action condition world model is a world model that, given a current state of the world, Sx, and an action you imagine taking, can predict the next state of the world, Sy. And you can train that system using observation data with actions if you have them. And eventually, you can probably use those world models to control complex systems that can be only modeled at the phenomenological model level, without, particularly for systems whose behavior cannot be reduced to a small number of equations. I took here the example of a turbofan engine, but it could be a chemical plant. It could be a patient that you're trying to treat. It could be a whole robot and its interaction with the environment. So a lot of applications for this in the physical world. And we're not going to be able to do this with generative models. And so that's the way we're training JEPA. We have a bunch of results on this using something called SIGREG, which is a regularization term that attempts to maximize the information content coming out of the encoder. I don't have time to describe what it is exactly. It's an idea of that has to do with making sure that the distribution of points that comes out of the encoder is basically isotropic Gaussian. More recently, we actually built world models based on this method. It's called Le World Model, and it uses the SIGREG regularizer to train the world model. You can see the URL of the website here, where there is kind of some code, a few demos, and there's a paper, and this works reasonably well. I'm not going to show you demos or anything, but there are predictions of sort of various situations in robotics or simulated systems. It's still at a relatively small scale, but it works. And it works relatively well. So I'll conclude right here. Can we build or train hierarchical JEPA models to provide us with essentially a way to build universal causal models of any complex systems that we observe through measurements and sensor data, including things like human cells and organs and bodies, but also complex systems, manufacturing plants, or whatever else. And that's the challenge, I think, of AI for the next few years, and can we use this for planning? And I'll stop here. Thank you very much.
better now? Okay, thanks a lot. Okay, so it's time now. Thanks, Yann, it was very clear. So I think there is a lot of debates between being generative or not generative. So I think we can start with that. I think I will leave the floor to Eric first, and then we'll take a question for audience. So Eric, first, what are your first reaction on Yann's vision on a world model and embeddings and prediction in the latent space?
Yeah, well, first of all, thank you, Yang, for the excellent presentation. To be honest, even though people thought it's a debate, it's probably, a venue for us to seek, common ground and build consensus, and also maybe enlarge, the methodology toolbox. Because I fundamentally agree with Yang that the prediction, of course, needs to happen in abstract space. Yeah, I think there are some technical issues about how to validate the prediction, and also how to make the full pipeline, consistent and end-to-end. Because at the end of the day, one function of the world model, is to generate contents, and you use a plugin, on top of the system, the encoders and the reasoners, with a new plugin of decoder, or it is an end-to-end system that can be trained and also validated at the same time. I think these are technical points I want to maybe elaborate a little bit, and I'd love to hear Yann's thoughts as well. So I think we pretty much started the same from here, right? So we need a world model, to be, a simulator, to really train agents, with a lot of possibilities, and that's essential. And it has to basically predate, the arrival of a truly capable agents. And then here, I think I summarized Yann's points, quite carefully already, and I'm not going to repeat. So I'm going to now offer, maybe a point-to-point, rebuttal of some of the points he made, and offer a slightly different view. First of all, I think it is really two design choices between JEPA and GLP. JEPA, is to really implement, a latent space. That is what I called a partial reality due to purely unsurmountable numerical issues. Because when you bring the information, from the observation data through encoder into latent space, it's a lossy encoding, and it is very hard to recover the information unless you reconstruct where you come from. Whereas the GLP is a full pipeline of a closed loop of encoding and decoding. The purpose is not to generate, but the purpose is to use the generated outcome to validate. Therefore, there is a chance for a subspace that is compatible, or maybe even equivalent to the true reality space. But now let's get to the points. Data. Yang mentioned about the importance of video data, which I totally agree, and I'm going to maybe add one more dimension to that. I think video data is useful, but it also can be misleading, and therefore it's not adequate. For example, we all see this picture. It's a very, very famous picture, in the 70s, which generate a huge movement in the US. Because what we see here from the pixel is really a person kill another person. What is not known, because this is the direct kind of interpretation from the video model only. Someone kills some other people. But if you know the context, of this whole story beyond the video, you actually know that this one being killed, is actually, a criminal, that kills civilians, and the shooter is actually, a general that is, catching him. Again, the context is not available in the video. That's why I say when we train world model, the video itself is not providing the word knowledge entirely. You need to have additional information of text. So that's kind of my simple answer to the data usage. Representation, likewise, I think only based on encoder generated continuous signal without using the symbolic knowledge offered by the words is also inadequate. Because, for example, we want to infer, this long-term, event of apple getting rotten over the few months, without the support of, the text for symbolic reasoning. It's very hard to use the visual kind of simulator to generate that kind of possible words, right? And there are other things like a counterfactual, reality, or not reality, but possibilities and agent interactions, which actually leverage on the fact that we humans use visual and also lingual approaches to interact and also to reason. Therefore, I think on the representation level, the fundamental reason for me to advocate a mixed representation, continuous and symbolic, really is out of that concern. Now come back to the architecture, which is Yann's core argument. This is basically the encoder strategy, which makes a world model to be a predictor of the next latent states. Yann already mentioned about the numerical, collapsing issue, right? Which again, I'm not going to talk too much, but I want to elaborate on what is behind it, due to this collapsion, and also, where issue can be fixed. So in the encoder, decoder strategy, I think what's happening is that, as Yann mentioned, you can easily have a trivial encoder to put everything into a constant and still make good connections. And but the core kind of design here is to really turn encoder into a predictor rather than a transformer of representations, because they need to create a representation that match the next representation that is also produced by an encoder. So their eventual function is a prediction function. And when you have a prediction function, you inevitably have information loss, because whatever useless for making the good prediction will be discarded in the encoding. And that information loss is very hard to recover unless you have a different objective which will be making use of that information. And that is why a generative approach is kicking in, because in addition to make the latent prediction good, that prediction also need to be reused to produce the actual observation data, which actually requires you to keep more information, even though they may not contribute to the prediction of the next latent states, but they may be useful for predicting or generating the next image, which exists in reality for verification. Therefore, there is really a divergence, or maybe a difference on how information can be preserved or can be discarded. The generative approach allows you a way to do full reconstruction and therefore keep all the information in place, regardless whether they are predictive or not in latent space. And that leads to basically these two pathway, toward the full maybe journey of the data, right? On the JEPA path, you'll start from observation, and you are likely to have a lossy encoder, which leads you to a incomplete latent states. And then, you will be building a predictor built on that states. And then, that predictor will be, used for predicting the next one before, in fact, ever it come out to match with the real data. But on the other hand, the GLP approach, technically, gives you, a closed loop where whatever next prediction need to meet extra qualification, in generating the observation. Now, one, major, critique, as Yann mentioned about making the next pixel or next image prediction, is that the impossibility. It's too complicated. It is not necessarily even predictable. That part, I think there are, how should I say, it's maybe an intrinsic difficulty that lies in the very interesting essence of world modeling, that how to basically make that so-called unpredictable thing actually predictable, either through architectural design or computational innovation. Because if we choose to make predictions only on the thing that we believe to be predictable, then that importance of the subset of information to be predicted is governed by the training data you use. And then when you train a model, you basically already use the training data to define what is important, in latent prediction. But when you go to texting data, the generalizability issue is lost, because you really may already lose the information, when you establish good latent predictors on the training data. And therefore, the saliency, who defines that is something, that is, sensitive in the case of a JEPA model, but less sensitive or maybe even agnostic in a generative model. Efficiency is another issue. I already in my talk show a number of examples about how to construct smart decoders, which can partially, generate, salient information or important information, in the output and allow them to be validated. And also there are recent development which actually allows, for example, a very, very fast video reconstructions, at a time that is even 10 times, 1/10 of the time the video rollout can play. So there are engineering issues that one can use to actually circumvent, some of the computational issues that, one can. Sorry, I need to look for a particular page. Okay, so I think that's where my main point is. I would say the completeness and the correctness of information is not to be compromised. To be trade-off with the efficiency and the computational resource, because those issues are engineering issues which can have a continuous evolvement. But the architecture itself, if wrong, then you lost information permanently and cannot be recovered. And last but not least, I want to say a few words about the reasoning, because of this focus on both generative capability to produce long-term consistent signals to be validated. We have the opportunity to test a word model which should be tested in that way in long-term consistencies and also planning capabilities, which requires obviously a richer set of latent representations, both for system 1 and system 2 reasoning. And the latent encoder, the latent predictor based on encoder init structure is very, very difficult for us to extract representations of that granularity in a flexible way to enable those long-term consistency inferences. And also, there is another engineering issue, which we found to be very interesting. The GLP architecture, which is a encoder-decoder architecture, make use of many existing tools, such as existing strong VLM-based encoder and diffusion-based decoder, and also LLM or diffusion-based reasoning backbones. That actually make the system open to many of the existing work. For example, our recent speed up of the video jam took advantage of a very fast large language model K2 that we developed ourselves, not originally even for this model, but they can be plugged in. On the other hand, a latent space predictor word model had a representation that is very, very difficult to interpret and be compatible with existing systems built elsewhere by other teams. Therefore, it is tricky, to really, build a sustainable, toolbox, to, systematically, ramp up the size of the model, and also to make use of, other, training strategies and, modules available elsewhere. So I want to wrap up by showing some of the, evaluation benchmarks I already mentioned to invite, community to benchmark and measure the word model in a more careful way. Because even, from the results I just see, and also from many of the results that we had in the past, much of the benchmarking of the word model are still not quite in place. They focus on visual capability and the visual generation rather than task solving. So this long-term consistency and the planning quality is something that has been so far ignored, including, for example, in the recent VJEPA paper. We do find that the validation, are really still focusing on, more visual, computer vision type of tasks of segmentation and object recognition. And also the interface, obviously, is a little bit difficult, for language models and other models to be kicked in. I would wrap up by saying that these type of new tasks which we recently published, to hopefully call for a new platform to validate, what model functions can be tested, for the capability of new world models. I think, for example, here, continuous branching, of simulations, and games, that can create different possible worlds for different agents, are where I see, a greater possibility, to try out either JEPA, or GLP in terms of their generalization power. So with that, I want to wrap up by maybe summarizing some of the takeaway points where Yann and I could deliberate and maybe make additional comments. I think the real, kind of angle, divergent angle from Yann and me, first of all, we agree we will be working on latent space, but the representation, should it be stateless, stateful, continuous or discrete, is where technical implementation make a difference. Then the role of decoder, it could be viewed as a distraction, obstacle because of the unpredictability of a complex content. But if you flip the coin, it could also be, a challenging validator to provide a closed loop, through action facilitated latent reasoning over realizable world states rather than just imaginary world states. And of course, the reasoning part I said already can be a mix of symbolic and numerical reasoning. And there is also the mathematical issue. Regularizer is a little bit difficult to characterize. Therefore, we need to carefully design the regularizer to make even the training itself computationally nice behaving, whereas the GLP generative model does not, suffer from that kind of collapsing, or degeneracy issues. From the user end, the debate between, Yann and me seems to be catching a lot of attentions from the non-technical world, which didn't care really about what technology we use. They care about the functionality. And I want to single out a few functionalities that has been really, really, highlighted. For example, people want to see a model to be able to generalize into unseen words. And Yann also mentioned about the generalization to the unseen is very, very important. And here, the approach between JEPA and GLP really are radically different. One is a latent space optimized for predicting unverified latent states. But the GLP is really, built on, what hopefully can be a lossless encoder and in tandem with a reconstruction decoder that can unfold the compatible but the previously unobservable future. Therefore, I think that function are more likely to be realized. Long-term horizon latent stability is also very important, and our approach is to use, again, observation as a guardrail, whereas the JEPA approach is heavily relying on a good design of the regularizer. The training and deployment, as already mentioned, one is a more assemblage, of available tools, using standardized representation and the latent architecture, and the JEPA is a little bit more, less kind of transparent in terms of how to interpret the internal representation and how to port those representations into additional models. So these are just some observations I want to put here. I think without really elaborate too much, I see these two pictures to be contrasting a JEPA and a GLP. Reasoning in the latent space is to me like sitting in a monastery, doing meditation and thinking through all the mental exercise. But on the other hand, regenerating the observation data in the training through latent representation predicted from the previous one is more like a missionary working in the field, constantly interacting with real world and people. Obviously, there are a lot of misinformation, noise, and so forth, but it's a different way of learning. And which one is better? Well, we need to let the results, to tell in the end. That's my answer to Yann's presentation.
Thanks. So now, Yann, it's your turn,
and then we'll give the room question for the room. So Yann.
Okay. So Eric makes a number of good points, but I'll turn this into a rebuttal to make the debate more interesting. So first of all, you're absolutely right that JEPA produces a partial representation of reality. But my argument is that this is an indispensable feature. It's not a bug, it's a feature. The world is messy and noisy, unpredictable. Most of the information in the world simply cannot be predicted. In fact, physicists even have a name for this. They call it entropy. Let me take an example. If I give you a box filled with air, there's not much you can say about it. But one thing you can say is that if I start heating up the box, the pressure will increase. Okay, and in fact, we have a formula for it, PV equals nRT. Now, this is a very abstract representation of an incredibly complex underlying process where you have a ridiculously large number of molecules bumping into each other and bumping onto the wall of the box. And that creates pressure, right? And the more you heat the gas, the more the molecule move fast, and it creates more pressure. Now, nobody has ever been able to actually simulate this at the level of individual molecules. It's completely impractical. And so, you know, in physics, we call this entropy. And that allows us to ignore all the irrelevant details and just work at the level of things that we can predict, like PV equals nRT. If we increase the temperature, the pressure will also increase. And vice versa, by the way, if you increase the pressure, the temperature will increase. So, you know, we cannot predict individual molecule positions. It's useless. It's way too expensive. It's completely impractical because we can't even measure the positions. Therefore, we absolutely have to ignore details. There's no way around it. It's the only way to understand reality is to ignore details you cannot predict. So that's exactly what JEPA is designed to do. It's designed to find a trade-off between extracting as much information about the input as possible, but also to minimize the prediction error. So as a result, JEPA extracts only the information that it can predict and ignores all the information that is simply not predictable. It's exactly what we do when we model a complex physical system. We ignore the details that we cannot predict. We call this entropy. So there's a very fundamental thing to this also, which is that if we want to make long-term prediction, we have to ignore more details about the prediction. If I try to predict individual molecule positions and velocities, I'm not going to be able to do this over the body of an airplane or even a wing of an airplane to compute drag and lift. I'm going to have to find an abstraction where I cut the air into little cubes and I represent the state of the air into each cube by a velocity, a pressure, and a temperature. And then I solve Navier-Stokes equations. That's an abstraction already. When we want to figure out the effect of a drug or something on a human cell, we don't actually simulate, at the level of density functional theory or molecular dynamics. We do that at a much higher level with biochemistry. I'm going to use your car crash argument. You say, I mean, the argument about the car. You say that it's better to kind of preserve all the information and reconstructing because you never know what information will be useful. Whatever information you cannot predict is not going to be useful. I guarantee that. And so that's exactly what JEPA is doing. It says, okay, there's a lot of things I cannot predict. And since I cannot predict them, I'm not going to be able to use them for planning anyway. So I should as well ignore it. A generative model like GLP is going to have to when you have a car that drives along the road, it's going to spend a huge amount of resources modeling an enormous amount of detail, like the random motion of the trees, of the leaves of the tree bordering the road on a windy day. And that's, you know for a fact, it's not only completely useless, but it's also completely unpredictable. If you attempt to train your system to make those predictions, you kill it. It simply doesn't work. So that's the argument for the fact that ignoring details by not attempting to reconstruct is and producing abstract partial representations of reality is a feature. It's not a bug. It's a feature. It's necessary. We have no other way to actually do that properly. In fact, this is very connected to the notion of invariance. When you have an encoder that represents, produces an abstract representation of reality, it eliminates details about the input. This is the same phenomenon that happens when you train a classifier or you train any kind of machine learning system, a multi-layer machine learning system. It learns hierarchical representations in such a way that not all details are preserved. Only the details that actually are useful for the task are preserved. If it's a supervised task, for example. And so, again, the trick there is how you eliminate all the variabilities on the input that are irrelevant for the task, right? If you do handwriting recognition, the style of a character is irrelevant. So you want a representation that is invariant to the style, maybe to the size of the characters, maybe to their orientations and distortions and noise and things like that. It's the same argument. If you want to make prediction, you have to eliminate all kinds of details of this type that are irrelevant, and the way you define irrelevant details is details that you cannot predict. You had an argument also about the advantage of using text. Of course, that's an argument that applies to humans, doesn't apply to most animals. They don't have language. They understand the physical world pretty well. They can construct abstractions. They can do hierarchical planning. They have world models. There's no question about that. So you don't need text, but if you have text, you might as well use it. And there is no objection to using text in the context of a JEPA architecture. It's entirely possible. And I'll stop here.
Eric, now.
Well, thank you, Yann. Very, very insightful comments. I think that there isn't a disagreement that you want to keep only the useful information, for the prediction. And also, the latent prediction is using a subset of information for making that prediction. I think that the major divergence are maybe 2 points. Right? One is about how to ensure that that prediction itself is correct, and also how it's useful. I slightly disagree that whatever that is not predictable is useless. In fact, if a medical doctor, we take tissue samples, we take the sample and we keep it, even though in my first experiment I may not understand all the nuances, but I can always go revisit. In a sense, when we pre-train a model, we not only wanted to limit itself to something that is immediately predictable, but also to have a trade-off of something that have high value and it can be still kept. And in the GLP approach, the observation is now automatically used as a mechanism to have a voice in terms of what information is useful, in addition to being useful for making the latent prediction, but also in reconstruction. Then reconstruction, of course, is always a very, very how should I say, diverse or wide definition. It's not necessarily a pixel level, match to match, right? It's also, about, maybe more information-rich representation, that you want to recreate to sanitize and validate the latent prediction. So in the practical implementation, we still are trying to prevent, for example, issues like hallucination, and also the balance between pre-training and post-training and fine-tuning. In the JEPA approach, it is challenging, to rely on a pre-trained model that is filtering out, most of the information that is not directly, immediately, predictable, in a particular type of data. For example, I want to train data, based on car and certain scenarios, but there are other informations, of the view and maybe other dynamics. When you discard it, it does make a good training model for that only car movement function, but it is very hard to generalize. Therefore, it cannot be a very general purpose model. When you fine tune it, for a downstream application, those information has to be relearned, right? So I think, there is always a balance where, having the GLP architecture, actually GLP can strictly subsume, the JEPA if you turn off that generative function. And also you can also, reweight the generative function in terms of how much you respect that in terms of the reconstruction loss. So that's, but on the other hand, it opens the door for looping in the reality so that you don't hallucinate for too long. And also you allow a flexible time span in terms of coming out, from the latent space and validate not in every frame or every second, but from time to time at an affordable trade-off of computing and the resources, to create that kind of a balance and a guardrail on the quality of the latent prediction. In terms of the computability, I think, with the recent, dramatic improvement, of new architectures for sparse diffusion and sparse attentions and so forth, reconstructing, high quality images becomes a lot cheaper than 10 years ago or even a year or 2 years ago. So I would ask you if, you can very, very cheaply, reproduce or generate, information from the latent space to directly, leverage on, rich information in the data, in trained data, would that be an option, to enhance, a latent prediction architecture, with the benefit of additional information from the observation?
Thanks. So Yann, quick answer, and then I will and then I will give we take question from the audience. Okay, so question from the audience. Okay, just introduce yourself.
Hello, my name is Bahia and I'm a cybersecurity engineering student. And in my field is built on the principle of minimizing noise to find the threat. Dr. Eric, you've mentioned the Turing trap and the idea that we should focus on purpose instead of just mimicking a human-like generation. From an engineering perspective, it feels like the current push for generative models, word models, is an attempt to catch all fishes in one basket, aiming to protect every pixel or token, and ending up with a basket filled with irrelevant data. Considering the massive issue with data scarcity and annotation, why shouldn't we abandon the generative requirement entirely? Does the panel believe that a non-generative representation-focused prediction architecture like GPA is the only viable way to reach AGI? Without drowning in the noise of data-heavy generation? And specifically, is it time to stop forcing word model prediction to predict every pixel as a primary goal and instead move toward a hierarchical approach where non-generative GAPA core handles the underlying logic, and at the same time, pixel generation is only treated as a secondary task-specific layer?
Yeah, thank you for the question. I do want to make a very, very explicit clarification The goal of the GLP and the world model is not about predicting pixels. World model has its own function, as we both Yann emphasize. It's a simulator for what possibilities for reasoning, right? So it's like you train a student in university. You need to put examinations. It's just a new form of a particular form of examination which connects the model, in its ability to produce certain real world data. But the goal, the evaluation you'll see, not the training score, but the evaluation of the model you can see, from our work is on planning capabilities and long-term consistencies. There is no such a score that we actually use to measure pixel level reconstruction. This is a training score, not actually a evaluation score of the model. So that's something I want to make clear. There has been a lot of confusion right now, really taking generative model to be, the only purpose for generative model is to generate pixels. No, that's not. Generative model basically has many, many other purposes, and producing pixel is a validation score that we use to qualify some of the generative aspects or the model aspects.
Yann, perhaps a comment?
Well, I mean, the question was a little bit loaded in the sense that it basically made my argument. So I'm not going to contradict the person asking the question here. I obviously am in favor of only representing the information that is predictable and eliminating things that is not predictable, which in many cases is a way to characterize noise. That's what we call noise, or entropy in physics.
There's a question.
Yeah, thank you. My name is Khalid Taha. I am the co-founder of Tabshura AI Lab, Trafalgar AI, and Toot AI. It's quite inspiring to listen directly to both distinguished figures, Yann and Professor Eric. My question is, I'm really struggling to understand this deeply non-linear world, chaotic, complex, beyond complicated. And then whether it's GLP or JEPA, how can we claim that we're gonna simulate the world model? So are we shortened by coming up with a more realistic terminology first? And the second question is, how can we approach the such complex world with a linear algebra, or the computation, the foundation of the computation is based on a linear product of the human beings? So am I missing something here? This is the question. Thank you.
Well, I mean, certainly the models that we've been using now for decades in deep learning are non-linear, right? The main operations, of course, are linear operations, like matrix vector products and things of that type. But you have to have non-linearities in them, otherwise there is no point having multiple layers in your architecture. So that's the big, the big thing that took years to convince people in the machine learning community that having multiple layers of interspersed linear and nonlinear operation actually had intrinsic power that shadow systems didn't have. I used to have that debate with people, including with Eric's PhD advisor. Michael Jordan, way back. This was 25 years ago or so. So the fact that at the bottom we use linear algebra is irrelevant to this. We basically have ways to approximate complex nonlinear functions. That's what deep learning is used for. Now modeling complex systems, there is a number of systems that we can reduce to a small number of equations. This is the traditional way of building models. You study a system, you figure out what are the relevant variables, and then you write down a bunch of differential equations generally if it's a physical system, and then you can simulate at some level of abstraction. You can simulate the behavior of the system by solving those equations, by integrating the differential equation. So computational fluid dynamics is an example of this, right? You can simulate the flow of air around an airplane using this, Navier-Stokes equations. But in fact, it's almost too accurate to be useful. What you really want in the end is just a few numbers about the characteristics of the airplane, like drag and lift. If you could actually directly predict the drag and lift using a neural net, from the shape of the airplane and the speed of the airflow and the angle of attack, you would pretty much have all the information you want. And so people are actually doing this. They're building neural models to directly predict the variables they're interested in. They're not trying to predict the next state. They're just trying to predict the relevant variables. And so that's a way of kind of simplifying the problem. But then we're getting outside of the domain of self-supervised learning, because that becomes supervised learning now, right? You have to have the data to train your system to make those predictions. Self-supervised learning is the context in which the data you train the system on does not have any human provided labels or outputs, but basically the output is also the input, right? You're predicting part of the input from another part of the input. For example, predicting the future from the past, right? That's what self-supervised learning is based on. But to handle complex systems, what we need are phenomenological models of those complex systems that ignore all the details that we just cannot predict. Again, we're not going to simulate a oil refinery or a chemical plant at the level of molecules. We just can't do that. We're going to do it at the level of, a very abstract level. Like, what happens if I change this control variable in my chemical plant or my power plant or my turbojet? What's going to happen to its state? Can I plan a sequence of actions to bring the system to a particular state? We're not going to be able to do this either for human cells or let alone for human bodies. What sequence of drug or treatment should I plan to bring a particular patient, to control the blood sugar of level of a particular diabetes patient? It's a planning problem. You need a model of the patient for that, and it's a very complex system. You're not going to reduce it to a small number of equations. You're going to have to train it from data.
So we have,
Yeah, I want to add to what Yang just said. In fact, complexity can come out of a very, very simple systems, as Yang just mentioned about the aircraft and thermodynamic, fluid dynamic simulations. If you look at, for example, the game of Go, the rule of Go, can be written within one page, but it generates already infinite complexity. So the potential, the capacity of the world model isn't really lies in how complex the model is. It's really about how much insight it can learn from data, and then use it as a simulator. In fact, people compute atomic energy in the very early time using MCMC. It's actually based on very simple rule, but you can simulate already some of the critical physical properties of materials. I also want to add to what Yang just said in terms of again back to the importance of abstraction, and also in my opinion, also equally, if not more important, a qualification of the abstraction. We need to stay, of course, with the proper abstractions, to make, to be actionable, and also to really, really make useful predictions. But then there are many abstractions, which may, if not verified, have a verifiability issue. When people, learn physical knowledge and biology and so forth, and extract perception, these are interpret knowledge. People can actually, build knowledge upon and do something with. But using a model, to learn automatically isn't guarantee you identifiability and also, consistency. That's why, in my opinion, validation through generation is a critical path. We use, for example, validate physical laws by making predictions of the position of the star. and therefore we go to the star and go measure and compare the differences. That's usually how a abstract theory is established. But in world model training, that link right now is not yet in place if we ignore the generative part where the real observations are brought in to validate the latent laws and latent predictions.
I like your example of predicting the position of a heavenly body, because there is an interesting point about this. If I give you all the data that we've ever learned about Jupiter, it's an incredibly large amount of information. A lot of it has to do with the weather, the dynamics of the planet, the atmosphere, radiation, magnetic field, all kinds of stuff, right? But if I ask you to predict the position of Jupiter in 100 years, you only need 6 numbers. You need 3 positions, 3 velocities, and you can predict the position of Jupiter in a century. And so that's actually precisely a perfect example of the fact that to make predictions, you don't actually need that much information most of the time. You need to extract the relevant information. I mean, the genius of Newton was to figure out what is the right representation of positions of planets and their dynamics, and the fact that the entire state of a body in motion is basically positions and velocities, also rotational velocity. But let's ignore that for a moment. And then put yourself in a reference frame, figuring out that the planets rotate around the sun and things like that. So that's a perfect example of what allowed people to make accurate prediction about the position of planets was precisely to figure out the appropriate representation for position, basically relative to the sun, realizing that planets rotate around the sun, and then deriving very simple rules for the dynamics. And it turns out the relevant variables are in very low dimensional, very simple.
Absolutely. I think there is one dimension is about we do not always know what we actually need to predict and want to predict when we do that.
Right.
For example, in astrophysics, this discovery of the redshift, and it's not because they are collecting the redshift data. They don't have this concept yet. It's just collect the background data of the universe, and then suddenly find a mismatch of the data with the actual kind of calculated outcome. So the way I see latent representations to be inclusive and informative is that they don't want to too strictly build on current prediction, because one of the users was asking how to generalize the world model into unseen words. There are utilities of the world model that we don't even know, and you want the information to be in the representation so that they still can carry out into extrapolated functions and maybe unseen universe.
No, I agree that if you don't know in advance what information is going to be useful, you want to extract as much information as possible. But my argument is that there is no point extracting information that you cannot use to make predictions, that you cannot predict. It's going to be useless anyway. You might represent it, but if you can't predict the dynamics of it, why extract it? You're not going to be able to use it to make predictions. And so
the definition of prediction lies in my opinion, the observation space, not in the latent space, right? Because we predict the star.
Okay, so that may be where we disagree.
Yeah.
That I think predictions should be performed in latent space. And of course, it's a trade-off, because if your representation is not informative, then prediction becomes trivial. So there's a trade-off between maximizing information and minimizing prediction error. And this is exactly what JEPA the JEPA training criteria are doing.
We have time for 2 questions. Only 2 questions. We have 1 question there. Okay.
Hi, Eric. Hi, Yann. Alain Rosen, Dean, École de Pont Business School, and also Professor of Innovation. And more importantly here, I am the self-designated representative of the laymen who are in the audience. I'm wondering if there's not a deeper, even though it seems like you agree on a lot, but there's a deep philosophical difference in the signal and noise approach. It seems like, Yann, you're seeing mostly noise in a messy world, And just like the Jupiter example, you only need those 6 data points. That's the only signal. Whereas Eric is saying, no, everything is signal if you know how to look. And if we go back to the video that you showed at the beginning, Yann, that you've been struggling with for 10 years, it seems like Yann is saying, I'd prefer a blurry video over what Eric might want to see, like a perfectly pixel perfect video that shows the girl not blowing out a birthday cake, but spitting an olive pit. And I'm wondering if I've understood correctly your philosophy on this.
Partly, yes and no. So I don't prefer a blurry video. In fact, the fact that when you force a system to make a single prediction, it produces a blurry video is a sign that you really cannot train a system to produce pixels if you make point predictions, so a single prediction. So of course, the argument against that is to say, well, don't predict a single point, predict a distribution over videos. The problem with this is that you cannot accurately and usefully represent distributions over the set of all possible video frames, let alone the set of all possible video clips. We don't know how to do this. We generally, when we want to represent a distribution, we go through an energy function, and then we do what's called a Boltzmann distribution. So you do exponential minus the energy, and you normalize, and you get a normalized probability distribution over the space. But generally, this normalization is intractable. In high-dimensional continuous spaces, you simply cannot normalize useful distributions. So that's what led me to a formalism called energy-based models, which basically is kind of a weaker form of probabilistic modeling. But what I've tried to do and failed was to basically use this kind of techniques, modeling distribution approximately, or using energy-based models to make predictions at the pixel level. Now we have techniques like diffusion models that work better than the stuff I was working on 10 years ago, but it's still very imperfect in the sense that the diffusion model will produce a nice looking picture, but there is absolutely zero guarantee that the model is not what's called mode collapsed, which means it's going to produce pictures that look like the ones that you trained it on, but it does not actually represent the whole set of potential legal images. And so I had this epiphany about 5-6 years ago, where a little more than that actually, when I realized like you really do not want to predict pixels, and the main reason that made me kind of switch my opinion about this is that we had tons of experimental results on training self-supervised system to represent images. This is not video. This is you take an image and you transform it or corrupt it in some ways, and then you run the original image and the corrupted image through encoders, and you try to make the representations identical of those two things, because they're really two different views of the same scene. And so the representations should be the same if you want them to be invariant to those transformations. A lot of people were trying to train vision systems in a self-supervised manner through reconstruction. So take an image, corrupt it or transform it in some way, and then train some big neural net to reconstruct the original image. There was a huge project at Meta on this called MAE, Masked Autoencoder, which is a form of denoising autoencoder. And diffusion models are kind of a form of that as well. And that project basically failed. There was a huge amount of resources that were devoted to this project, and the representations that were produced by those systems really were not good. People are using, VAE, VQ, VAE, all kind of, masked autoencoder or denoising autoencoders. None of those techniques ever produced competitive representations using for images, like none, absolutely none. The only methods that ever produced competitive representations for image understanding are all joint embedding architectures that do not attempt to reconstruct. And the empirical data on this is incontrovertible. There's like tons of evidence, including things that actually Eric mentioned in his talk, like Dino. The Dino features are trained without reconstructions. In fact, that's one of the big advantage. The IJEPA, VJEPA features are trained without reconstruction. Moco, SimSiam, SimClear. There's a whole menagerie of methods of this type, where the representations seem to be giving pretty good performance, but none of them is trained by reconstruction. All attempts to train image representation by reconstruction have failed. And so it's a pretty clear signal that you should not reconstruct. It's very, very clear. It's empirical. It's not Yann's intuition. It's hard data.
If I may add to that, first of all, thank you for the question. I want to approach your question from two angles. One, as you said, a philosophical angle, what is noise, what is signal? And the other, of course, is engineering issue, how to really make the prediction efficient. I was originally trained as a biologist. In biology world, biologists are very opinionated. They have a strong opinion about what is noise, what is bad data, what is good data, and so forth. I've always been a good advocate of all data are good data, because even if it is not pointing to the signal that you want to predict, they point to your behaviors and maybe platform, systematic errors and other instrument errors and so forth. And in the past, we don't use that because our technique, our ability to model this data are poor. We use a linear function regression to model biological data. But now with transformers and the foundation models, the attitude has been changing. If you look at how people train large language model, for example, there is no bad data. Data are all thrown in, and they basically settle by themselves in some way, unless you really want to have a guardrail of behavioral alignments and so forth. Otherwise, you take all data. I think, first of all, in here, I want to have a model, a framework that has an open kind of, position, on what is important, what is a noise, and what is a signal in the data, so that my representation can accommodate what may be needed in the future, even not now. That's a kind of a philosophical position I want to clarify. Now, on engineering part, in fact, I'm coming much younger than Yann in terms of witness the history of technological bottlenecks in the past of making pixel predictions and the video matching and so forth. But I also witnessed that in the past several months, or years, this reconstruction, technology, fueled by stronger diffusion models and maybe a next generation model to come in the next couple of weeks or months, who knows, will continue to improve our capability of making the predictions. So in a sense, I want to make sure that the model architect itself is not a function or a bottleneck of current technology, our inability, to compute, video generative data or pixel generation. In the sense, if you have, a 10 times or 100 times more powerful, and which is happening right now in some of our collaborative research, you want to quickly, benefit and leverage on those new information. And in my opinion, using a reconstruction error is one of the best way of using those improved capability of computing and architecture to make use of observation data.
We take a last question and then we wrap up.
Hello everyone. So it's
Short one.
Sure.
We can hear you.
Short one. Okay.
Fine.
So I'll be fast. Okay. So don't you think that the current testing techniques and metrics are not as compatible with world models? Also, if the concept of helping models, quote unquote, think in a worldly manner, but not being limited to text or to interact with the world, shouldn't we borrow some tricks from our own brains by abstracting multiple concepts or ignoring them momentarily to interact with whatever task is at hand to achieve AGI? And my last question is, if that's the case, how would you determine the concepts or informations to sacrifice, basically? Thank you for listening.
Okay, there's a very complicated question sort of implied in your question. So first of all, if we want to get to human level AI, we first have to figure out what does that really mean. I don't like the phrase AGI famously because I don't think human intelligence is general at all. So calling human level AI AGI, I think is nonsense. But clearly we want to make progress towards systems that have intelligent, human-like intelligence, right? Or if not better in some domains, we already have that to some extent. So intelligence is not a collection of skills. It's certainly not a collection of declarative knowledge, which is what LLMs are good at. LLMs basically store declarative knowledge. They do a little bit of reasoning. They can do a bit more reasoning in domains where the language itself is the substrate for reasoning, which means code, mathematics, and perhaps law, but that's about it. Maybe logic, if you train on synthetic data. But ultimately, you cannot measure intelligence by just the accumulation of knowledge. And so what do you measure it by? You can measure it by the speed at which the agent can learn new tasks or can accomplish new tasks, okay? So humans are capable of accomplishing new tasks zero shot without actually being trained. We face new situations all the time in our daily lives, and we handle it without having to be trained for it. Of course, if we practice the task multiple times, we get better at it. But most of the tasks that we do every day, we accomplish them for the first time, or at least we accomplish them in the first time in the situation that they are presented to us. And this is what makes us intelligent. And then new tasks that are more complicated, like we're learning to drive or something like this, we need a few hours of training. But the point is, we only need a few hours of training. How is it that a teenager can learn to drive in about 20 hours of practice, whereas we have literally millions of hours of training data of cars being driven by humans? And when we use this data to train a neural net to clone the behavior of a human, it does not actually drive at the same level of reliability as a human. The reason being that the dataset does not have complete coverage of all the corner cases. And there is a very long tail of complex cases. And so what makes a teenager different? The teenager has a world model, right? The teenager knows that if you are driving next to a cliff and you turn the wheel to the right, the car will run off the cliff, and it's not a good outcome, right? Your world model can predict this. And so you don't have to try. You know that beforehand. And that's what allows humans to learn new tasks in a very short amount of time using their mental model of reality. And it's not a single level, it's not a model at a single level of abstraction. We have models at multiple levels of abstraction and levels of detail. That's what allows us to be smart. So we're now going to measure intelligence. First of all, we're going to have to invent our own benchmarks. And I showed some of them. Like the benchmarks we use are basically planning tasks. And sometimes out of distribution, so different from the ones that you train the system on. We're going to have to invent our benchmarks, but also we're not going to be able to measure intelligence with a fixed set of benchmarks. What we're going to have to measure is the ability of an intelligence system to handle a new situation it's not been trained on, and to measure how fast it can learn to solve it, essentially.
Okay, so
Well, I have very little to add. If I can add one more point. First of all, I agree with everything Yann said about super intelligence or AGI being a very, very hollow, empty word, and the actual challenge in the details. I want to add that there is one point in developing agent or agency, which is that current architectures isn't offering the ability to do self-regulation and deliberation in terms of what to plan and with what approach to plan and with what data to learn and to do inference. in a sense, even with the word model, when you invoke the word model to do reasoning, or you just use your muscle memory, to do a reactive response by itself is also a question of current systems. So I think word model is going to be an important element to open up, a new avenue, for training powerful agents, but it's still not going to be adequate, to solve, all the scenarios that we need. Just as Yann just mentioned, if you have additional data in text, in other modality, you need to use it. Therefore, the engineering design of the architecture in terms of compatibility and pluggability, of all these different functions actually becomes also very essential. So it's more than just a conceptual idea of putting, a different data modality, or different architecture together. It's also about the real, interface and also, generalizability of the system, that has to be now part of the equation. And that part, and I have to say that the academic community is at a disadvantage because of a very limited resource and also limited ability to coverage a wider scope. You need to have a big team, that covers every dimension, in a system to understand the knowledge. In that sense, I am very jealous about the Yann's, setup, that you were in such an environment and you are building a new environment of this caliber. I think this is also important, for collaborative research in AI, that one single professor, single team is very difficult, to address all these issues that we raised.